to discuss changes to the time scale, to look at whether or not we need to adjust the ages of certain events. Card for you too. And I stole your handout.
Oh, that's okay.
So this is truly a living document, and will continue to develop as we move forward and as we better understand what's going on within the geologic rock record. Now, I've handed back all of your cards. I strive to learn names very, very quickly. If I get your name wrong, please forgive me, but also correct me if I call you by the wrong name. Now, what I do with the cards is all of you should have gotten some comments back on your comments. This last time, I do review the cards immediately after the class to give myself some insight into what you learned, into whether or not we had a problem during class that maybe someone did not understand, and then I keep a record of them. I actually keep a file of scanned cards so that if we get to November and you're having difficulty, I can go back, scan through, see where maybe I dropped the ball in terms of instructing or where the problem may have started. It helps me understand your development as a geologist, your development as a person, your development as a student. And so please do write on the cards, even if it's a negative comment, please let me know. That's something that is critical to me. Your success is actually quite important to me. I want you to learn. Now that takes effort on my part, that also takes effort on your part. That's where this consistent daily effort model comes in. You should be looking at the materials, reviewing materials every single day. Yeah, and it's not something that you have to do all the time. I don't expect you to dedicate 24 hours a day to this class. You can't. But you should be dedicating time to each one of your classes every single day so that you can develop, you can understand the material, because this is material that you just can't look at once prior to the test and have any degree of mastery. This is material that you have to look at and examine daily. So one of the corollaries to the mantra of consistent daily effort is that it's perfectly acceptable to not study on days that don't end in the word day. Okay? So that's not very often. Now, we started last time just looking at some of the things that we work with in structures and structural geology. That leads us into the material that we have, because a lot of times when we were looking at that, we were actually putting it into some sort of a time context, a sequence of events. Something happened here, and we want to know how we can make observations in order to piece that history together. And so what I would like to do at the beginning is just look at a few more images from around the country that might be helpful to us in pulling out some basic principles. Now, hopefully, all of you recall every second of physical geology, right? And you recall Dr. Cornell talking about some of the basic principles for determining relative sequence of events. And we're going to try to piece those together. We're going to try to pull those out. But we're going to try to pull those out of images, real rocks, real systems. Okay? So let's see if this thing will actually start. Now, if you're in the lab, Xiaobo Liu is here, the TA for the class. Xiaobo is a PhD student in geophysics and is preparing her proposal, right?
Yeah.
Okay. She's passed the qualifying exams, preparing her proposal, so she's 80% of the way done with her doctorate. What we will be doing is we'll be meeting at Red Bud Valley at 2 p.m. If you have a class that ends at 1:50, just join us along the Bluff Trail. We will be spending the afternoon making observations for trying to come up with a geologic map of the preserve. I would ask that you carpool if you can. The parking lot out there is relatively limited, so it would be nice if we could get out there in maybe 5 or 6 cars rather than 16 or 17 cars. Okay? Now, when we look at the course notes, oh, yikes, what the heck is that? That's interesting. Okay, let's come over here and see if we can figure out what someone did. Screen resolution. Did someone goof it up? Let's go apply that. Oh, that's it. There, that's a little better. How's that? Oh, it went back. Okay, let's go there. Apply that. And keep changes. So is that clear enough?
Yes.
For us to see? So when we go to the course, first thing you need to know is that I monitor and update the course on pretty much a daily basis, so that you want to check it fairly regularly. I try to have a thematic image up that will be related to the topic of discussion for today. And since today we're really going to be trying with the relative sequence of events, and since there was also an excellent question on how do you recognize the age of these formations? Thank you, Jamie. That was a perfect question that you asked. When you're working in an area, you tend to develop an understanding of the geologic history, and so you start getting to the point, especially when you get to be ancient like I am, you get to the point that when you go somewhere, you can usually go up, that is Cretaceous Dakota, or Lakota equivalent. You begin to recognize formations across all of the areas that you have worked. And so this is one of the areas. This is the Pennsylvanian tin sleep. It is part of a Aeolian erg, a very large-scale dune field that had roughly at least 14 different episodes, sequences of erg development in this particular system. And on top of it right here at this contact, where we go from the tan color with the beautiful tabular planar crossbeds up into this reddish formation, that is the contact between the Pennsylvanian tin sleep and the Permian goose egg formation. Now, as a young geologist, if you had never been to this area, you would never know that. You would have to be there with some old person who has been there before to point out what that contact is and how we know that. How we were able to determine that this was the Pennsylvanian, that this was the Permian, based on either fossil content or some other sorts of relationships within the system. It's not magical, it is a learned, acquired understanding process. And so that's a perfect image, and we'll examine this in a little bit more detail later to try to understand what can we glean from this particular image in the system. When you look at the course modules, now last time this was relatively ample. I put up the time scale. That's in honor of our incipient quiz on the time scale. This is the 2015 version, revision number 1 for 2015. And just in case you don't know, the dominant change is right there at the Cryogenian. There are new age dates that were available that adjusted that by quite a bit of time here. So that's the dominant change on that particular timescale version. And that's still undergoing review. When we look, the course notes, now from when I log into the course, I see all of these. You probably won't see these down here. This is the introductory materials. The next section will be fractures and fracture systematics. Then we'll go into faults and fault systems. These course notes are ready and they will be released as we get into those materials. These will not turn off. This will always be available to you during the class. And so if you look at any one of these folders on here, this is really a module that contains all the information that you might need for that particular material. So I have the introductory notes here as a PDF that you can download. What I recommend, what I ask is that you not print those. I think that would be a waste of your printer pages because each of you has, what, 1,000 on your little queue for printing. Put that onto your computer, onto your laptop, onto your tablet, or even onto your phone to review. I have a set of introductory slides, and you'll notice I always give a handout version of that so that if you absolutely have to print something, print this. It's 6 slides per page, so it limits the number of pages that you're printing. So it saves you time. Then I have a general notes section written with a freshman level class in mind on time, a section of slides on relative time, how do we determine the relative sequence of events, a description of sedimentary systems, and the all-important Younging direction. When you're looking at a series of deformed rocks, there will be many times that you will not be able to determine easily which way up is. Am I looking at a section of rocks that is in a normal orientation? Has it been somehow overturned? And we use Younging directions. There are occasions when this becomes critical. There was a wonderful example when I was teaching field camp. This is a long time ago, and we got into an area outside of Canyon City, which was a metamorphic terrain. It was a roof pendant that had been suspended in the Boulder Creek batholith and then resuspended and remetamorphosed in the Silver Plume batholith, and so it was messed up. And my notation for it was VBB, very boogered basement. It contained a series of vertical quartzites that were roughly 2.5 to 3 meters thick, and in the field area there were 7 of them. And so the question comes up, is this a single layer that has been folded, or is this 7 successive sequences of quartz deposition that was subsequently metamorphosed? And we were able to reason it out using simple Younging direction and show that it's just one layer, but it was folded to the point that we could say, okay, Younging direction is this way, that's that way, we're looking at anticline, syncline, anticline, syncline, anticline, and able to reason that out using relatively simple techniques. Then I have the section on deep time, which is sort of a view of geologic time. This handout on evolution of the time scale, a copy of the most recent stratigraphic chart, the GSSP table for 2015, that's something that's going to come up relatively shortly, and then the most recent time scale from the Geologic Society of America is on here, as well as a series of links. And you'll notice time scale, you have several different resources online, and then there's a program here, Timescale Creator. Oh, and you'll see that there's a homework down here lurking that will ambush you on Friday. It's timed to appear on Friday. So it's a good idea to review, see what's going on in Harvey on a regular basis. And if you see something, have a question about it, send me an email, let me know. So that we can work through the material and learn how to think like a geologist, learn how to think like a structural geologist, learn how to analyze these particular systems. So that is the structure of the course. Each one of the modules will have quite a bit of junk in it that would help you, I hope, understand the material, understand what we're trying to accomplish in this particular system. Now, let's go back and look at a few, oops, that's the wrong one, images. Now, we left last time with a little bit broader panoramic view of this particular system. We decided that we could recognize folds here. We're looking here at, we're going to call this, for right now, we're going to call this an anticline over here. We're going to call this a syncline here. We can recognize an anticline because the rocks bend over and back down, so it looks like a frown. We recognize a syncline because the rocks bend up, looks like a smile. And so this would be an anticline-syncline couplet. But as we examine it a little bit more closely, is this a nice, simple anticline-syncline pair, or are there some odd things going on? There's some bizarre things going on here. When we look at this system, we can start either on the right side or the left side. Let's start over here. These rocks are oriented about like so. Looks like they're trying to bend over a little bit here. But as we walk in, let's say that we're Spider-Man and we can walk on that. We can't be Ant-Man because if you do scale modeling, Ant-Man wouldn't be able to see. As we come in, something happening? What's going on right here? We have a fault. And we have a localized little anticline right there. Is that anticline present there? What does that suggest about the system? Were all these layers locked together during the deformation, or were they slipping past one another? They're probably slipping past one another, and that allowed the localization of this little anticline right there, and this fault comes up and out. Simply goes off the page in this particular case. So this beautiful little rabbit ear, you remember that term from last time? As we come into the syncline, things look pretty good. Do the layers change the way they look? We're coming in here, if we just follow this one, we're going, okay, this is nice, thick limestone. What happens when we come into here? It really gets thinner. And so it's being stretched out a little bit. And the outcrop looks a little bit differently. So we would have to determine what's happening here. Is this plastically being stretched out, or is this being crushed up and sliding almost like a uncemented bunch of material? So that we want to try to understand what might be happening in here a little bit. Now we get into this, we'll call it an anticline. Looks like an anticline right there. Looks like an anticline there. But what happens? How many anticlinal hinges can you see? John?
I see two, but to your question, is there possibly another fault there that's dividing the anticline that gives you this shape right here?
I would think so. We're probably seeing a fault coming up through here. We're probably seeing another one right there. In the system, this localizes a very sharp anticline that goes up here. We isolate out, we have another anticline that goes up here. That anticline, something funny happens right there, and then goes off. This one comes up, dies out, and there's something funky going on right here as well. And so, even though We may not have the experience, even though maybe we've never been to the Kananaskis mountain range, looked at Mount Kidd. It's a beautiful drive, by the way. It's actually a lot of fun. You see lots of bighorn sheep along the drive, so it's well worth taking a drive through the Kananaskis. We can begin to piece together what types of features are we seeing. We can even begin thinking a little bit about process. How did that get here? In this particular image, we are in the tip line, very near the tip line of the Canadian Cordilleran thrust system. That is a thrust system that has well over 100 kilometers displacement, that extends for about 250 kilometers out back this way towards the west. And the tip line is really only, it's about right there. The tip of the thrust system. So this has a context of both process, but also what type of a system are we dealing with here. Now, one of the challenges that we face in geology is trying to put things into a time sequence of events. What happened first? What happened next? What processes might have occurred to give us a particular feature? So, if we jump a little bit, now we are in Rocky Mountain National Park. This is on the Alpine Tundra Trail. So we're standing here, I think we're at about 12,150 feet of elevation. And you come across this thing. Does anyone, who's had geomorphology? What is this?
Wind erosion?
It looks like it has been subjected to wind erosion. Do you know the term? What we would call this? Something other than funny rock.
I was going to say head because it looks like it has hair and then head.
This is a hoodoo. This is where we have a slightly more resistant material on top so that we erode and undermine this, and there may be a degree of wind erosion, there may be a degree of glacial erosion involved. Is there a contact here?
Yes.
Right where?
Here.
Where's the contact? Help me out here.
Changing color with it.
Yeah, right there. This down below is a Neoproterozoic intrusive rock towards the perimeter of the intrusion, so it is actually pegmatitic in nature. That is the Longs Peak granite. This material on top is actually older. This is the Paleoproterozoic XB biotite gneiss in the system. Now, I heard a and a few questioning glints of the eyebrow when I said that. Why? What were you thinking? If you were to go into this totally unknown and see this, which one would you think is older? Why?
Just
Superposition.
because of the superposition of it.
Okay, so we actually utilized one of our fundamental principles, the idea of superposition. When we see rocks that appear to be layered, we assume that the older rocks are on the bottom and that the rocks will become progressively younger as we go up. That's perfect for sedimentary contacts. But since this is an igneous and metamorphic system, we're really looking more at a cross-cutting relationships type of a scenario, not a stratigraphic relationships type of a scenario. So this was a bit of a ringer here. We're looking at a contact between a pegmatitic phase of an intrusion and an earlier existing rock. And it's actually a wonderful little window into that, because if you come this way less than 100 meters, you're back into all XB. If you go over the hill even less than 50 meters, you're all back into XB. It's just a little window of the Longs Peak that is exposed here. And it's a pegmatite chamber of the Longs Peak, because normally the Longs Peak is fine grained. These crystals are really quite large in the system. In fact, I think you can see a few specular reflections in here. So this thing is actually about 10 meters high. This is a mica that you can see at this scale. So that's a big mica. That thing is huge. So we have to think about how we're going to employ these relationships. Now, let's take a little bit easier case. We're in the Grand Canyon. We've come in the East Gate. Or, I'm sorry, the East Gate here. We are near what is called the Watchtower at Grand Canyon, and we're gazing down into the canyon. We know that we're near the Kaibab monocline, of course, because we can see the monocline start to develop in there. But there's something else going on. What's happening? Yes, sir.
Are you referring to the depositional area in the foreground?
Here?
To your left. There.
Nope. There's something intriguing.
Is it the like sutures, or it looks like sutures on the far cliffs?
Up here?
No, down.
Down here?
Yeah, those
Yeah, there might be something going on down here.
intrusions actually, right?
Well, probably not. If we think of this as a pile of sediments, which ones are the older sediments? And which ones are the younger? Okay, so when we're at the Grand Canyon, hopefully all of you at some point in time get to visit the Grand Canyon, because it's truly a spectacular place to go. You can see this tan sandstone right there. That is the Coconino, and that's diagnostic. If you've seen the Coconino once, you can always recognize the Coconino. You can be driving down the highway at 70 miles an hour and glance out the window and go, ah, Coconino, and keep going. It's a beautiful Aeolian erg that occurred. This right here is the Tapeats sandstone. It is Cambrian in age. We go all the way up into the Toroweap here at top. So we have, in this section, we have from Cambrian up to the Cretaceous exposed. But do you see something odd happening at the Tapeats level?
Which level is the Tapeat level again?
Tapeats,
Which level is that?
right there.
Okay. Thank you.
Comes out, there's a little butte right there, comes back around.
It's like it's
It's split.
yeah.
Well, let's think about this. Can you tell me what the orientation of the Coconino is?
East, west.
It's pretty much horizontal,
Oh, no.
right? Okay, now, the foreground here, we're looking kind of at an unusual angle down into the Hermit at this point. These are pretty much horizontal here. This is in the foreground. This is very, very close to us. What's the orientation of this? Is it horizontal? Hmm? So we're thinking about initial horizontality, because these rocks are typically, when we deposit sediments, we think they're effectively horizontal. But Harley has made the suggestion that these are not horizontal. Look at this. They're dipping. They're dipping off toward the east. let's think about this. We said these were horizontal. We said these were dipping. Did something happen here?
Sound like you have something above it or something.
Yeah, something happened between here and here. What might that be? Any thoughts? Do we need to do a challenge question on this? Have you guys heard the term unconformity?
Yeah.
An angular unconformity. Because what happened, what we're seeing here, is that these rocks were deposited first. These are older than the tapetes. Those were deposited, then they were tilted, then we eroded, and then deposited the tapetes on top. And so the sequence of events that we would have would be, first off, we deposit those layers here, and let me put this in the appropriate sequence. We deposit those older sediments, then those sediments get tilted, then those tilted sediments are going to get eroded along the horizontal plane, and then we deposit the tapetes and younger on top. So we first deposit these things, then we tilt them, then we have an erosional unconformity right there that is an angular unconformity, where these materials were truncated after they were tilted. I said that these were Cambrian, that the tapetes is Cambrian. That means those sediments must be older down here, Precambrian. This is part of the Precambrian system, Neoproterozoic, in this particular case. And so we have a series of sediments of Precambrian age that are tilted underneath this unconformity. This right there, that is called the Great Unconformity. What you see in Colorado, Wyoming, Utah, out into Arizona is a tremendous unconformity between Precambrian age material and Cambrian and Younger age materials. A lot of times you have sediment sitting directly on top of metamorphic rocks or directly on top of igneous rocks. In this particular case, what happened here was we had a tilting event, and we actually have a fault bounding this just off to our right. And so it's a tilt block that rotated down, we truncate, and deposit on top. So with that knowledge, now I'm going to ask you a tough question. As we progress this way, you'll notice that the tapetes comes into contact with different rocks. As we move this way, you have this set of layers here, you have this one here, you have the red out here. As we move from right to left, is the age of the rocks underneath that tapete sand going to get younger or older? Why?
Okay. As we move, let's say east to west.
As we move from east to west.
Okay, you're asking the rocks.
The rocks
Underneath.
underneath, yes.
Yes.
So are these rocks out here underneath older or younger than these rocks here?
Okay, older.
Let's piece this together. if we have a section of rocks that is deposited using initial horizontality, and now if we use superposition, is this the oldest or is that? So we go 1, 2, 3, 4. Now if we tilt that and then truncate it, so now I'm going to tilt this section and truncate that underneath my unconformity. 1, 2, 3, 4. As we move that way toward the west, we expect that these rocks will get progressively older and older. Does that make sense?
Yes.
So we utilized cross-cutting here because the unconformity cuts across. We utilized initial horizontality. We utilized superposition. Yeah.
So basically, the opposite end of the fall, which was created by when it was tilted, should be the older end.
Depending on the direction of tilt. In this particular case, this entire section was tilted down. So we would expect that bounding fault to be right out here.
But if it were tilted up, the older rock would come
it might
up.
be the other way.
Yeah.
John.
Okay, one thing they taught us at field camp with these back on, which you can't always use color as a basis, but in some instances, especially when you're looking at big picture, you can use it to follow trends and stuff.
Yes.
And as I
So
look
you
at
can
that,
see,
I can
yes.
see that the sort of reddish brown is below. And as we progress east to west, it stays below. Never, there's no invert, no over.
That's exactly right.
And so that's what I mean. I'm not thinking like that. It's like, okay, that's got to be older because we, even though it's tilted, it still was below what we started with.
Yes, we took a package and then we just tilted it.
Right.
And so this is still older. And so as we progress to the west, we would expect to see progressively older and older rocks underneath that great unconformity. Let's find out. Let's go to the west. We've gone here less than a kilometer.
You mentioned how this unconformity is within several different states in this region.
Yes, this is the great unconformity.
Are we going to talk about maybe what sort of massive erosion event created such?
Toward the end of the class, absolutely, we can. Basically, if you look at in short, if you look at the Precambrian history of this area, what you're seeing is a series of terrains of igneous metamorphic sedimentary rocks that are being accreted to the North American Craton. Our portion of the North American Craton that they're accreting to is the Wyoming province. You're looking at the Yavapai event, you're looking at the Mazatl event and the Grenvillian event. Here we're actually looking at a fragment of the Mazatl terrain that was metamorphosed, the Vishnu schist, and the variety of different things. You're looking at that in this particular system. And so we can try to put that into a context a little bit later in the class as we try to start piecing together the tectonic history of this region. If you're looking, if we go back to the Rocky Mountain National Park, we were in the Yavapai terrain. And it's a lot of fun to play around hiking, looking at different portions of the Yavapai to be able to look at it and go, well, here we're actually in the island arc. At this part of it over here, we're in the subduction zone that was accreted during that process. So Tim, that's a short answer. If we look here, has anything changed? Now, it may be hard to recognize the tapetes here. There's the tapetes level. So here's the tapetes coming out and around. You can see the rock layers dipping below. So by the time we get across here, what's happened?
Yeah, it seems like it went.
It looks like it's changed a little bit. that's actually the underlying schist that these sediments were deposited on. What we see in this area is something that looks like this. Here's our major unconformity, the great unconformity. This is the Tapeats level. We have the sediments dipping underneath, and then we have an unconformity. And so what we have down here is the Vishnu schist, and we have sediments, Precambrian sediments that were deposited, tilted, and then we have another cross-cutting unconformity. So we have unconformity here and unconformity there in that particular system. Beautifully preserved, beautifully exposed in the Grand Canyon. And you can see down below here, you can see the schists as well. What's this?
It's
a coconino.
A coconino, yeah, you said you know.
Obviously. So the principles that we use to try to determine those simple relationships and piece together a story about the geology of a region, you're looking at initial horizontality. You're looking at cross-cutting relationships. We're looking at superposition. We're looking at initial continuity as well in a system. We use those as our basic concepts. Sometimes we will look at fossil content and utilize the concept of faunal succession. Life forms become progressively more complex through time, and faunal succession is also a corollary would be that once an extinction event occurs, you don't see that organism appear again. And so the classic silly example of that is if we see a contact here between two rock layers, and in this rock layer we see a dead geologist, and in this rock layer we see Tyrannosaurus rex. You know, is there an age gap here? Mm-hmm. Yeah, big one. Because the Tyrannosaurus rex was wiped out in the Cretaceous extinction event at the Cretaceous-Paleogene boundary. And so we can recognize, just based on fossil content sometimes, what we're looking at in terms of age relationships. The last principle that we often use is the idea of inclusions. If we find an inclusion in a rock system, that inclusion is older than the rocks that are containing it. Okay? So that's how we begin to piece that particular story together. Please review the slides on relative sequence of events. Let me know if you have any questions from those slides. And if we need to, we can hurriedly go through those next period to make sure that we understand those processes. Okay? So, spend the remaining time on your cards, the reflection, what you learned, what your takeaway is. Yeah. I'm not sure what I did.
Hey, I'm John. John, you think you can give me transportation? I have class that ends at 1:50.
At 1:50? Where is this class?
In Chapman.
Chapman.
It's next to the John.
No, it's like, do you know where Helmrich is? Yeah.
I was wondering, yeah, I know what Helmrich is.
It's the one
Next to it.
past Helmrich.
It's next to Helmrich.
Okay.
Next to the John and Helmrich.
I've got a white rental car. What I will do is, you know that little back road behind, John Mabey, the road that leads up? I just need me back there and I'll take that back, yeah.
About one
That's
fifty,
it.
okay, right.
This is a fun field trip, so this one's sort of fun.
Alright, thanks, John.
All right.
Where is that?
Down here,
Oh,
what we have
yeah.
is from here to, this is a schist down here. So we have an unconformity going to this. These sediments on top are tilted, then we deposit these younger camera. Then if we just get progressively younger as we move up the section. Oh, underneath, what we're talking about is underneath. If we look here, we would go 1, 2, 3, 4. So as we go to underneath this unconformity, since these are tilted, we would get into progressively lower blocks. Because this is the Vishnu schist, this is Paleoproterozoic, this is Neoproterozoic, not Neo, I'm sorry, Mesoproterozoic sediment here. And this would be the case, and then this is Cambrian. Okay? Does that make sense? Thanks, sir. Thank you.
I have some questions.
Sure.
There's nothing shown on Harwicks, so I don't know why. There's no